So hi everyone, my name is Chris Swetnam and I'm a research associate with the Advanced Robotics Laboratory at the University of Hong Kong. And I'm here to tell you a bit about how we've been using ROS and integrating with the Atlas robot from Boston Dynamics. So the Advanced Robotics Laboratory is a new laboratory established less than 2 years ago with the goal of putting Hong Kong on the map in the field of robotics. We're a small team with only 8 full-time members, along with many students who've helped for a few months each over the course of the project. Our main focus right now is participating as Team HKU in the DARPA Robotics Challenge. I imagine most of you have heard of it, but in case you're not familiar with the details, here's a quick overview. So the DARPA Robotics Challenge is the latest in a line of ambitious challenges organized and funded by DARPA, and this time inspired by the disaster response scenarios such as the one faced by Japan after the Fukushima disaster. So the competition features 8 tasks to be performed by the team's robots, including difficult terrain to be navigated and challenging manipulation tasks. There was a virtual robotics challenge using Cloud Sim last summer, and the robotics challenge trials were held at the Homestead Speedway in Miami last December. I'm not certain of the exact number of teams still in the running right now, but I think there are about 6 teams competing with their own robots and 7 teams using the Atlas, including Team HKU, but as mentioned previously, we're the only team to have purchased the Atlas ourselves. So Atlas is currently configured, has 28 joints, including 6 degrees of freedom in the arms. It's hydraulically actuated with an onboard computer that provides several built-in behaviors, including balancing and walking. It's designed to be used with a multi-sensor cell head from Carnegie Robotics, which combines an IMU, stereo cameras, and an FPGA for onboard stereo matching, and a Hokuyo laser scanner. The wrists on Atlas have 6 degree of freedom force torque sensors, and a choice of hands. Most teams received 1 pair of hands from iRobot and 1 pair of hands from Sandia Labs. Since we were purchasing parts ourselves, we were only able to purchase the Sandia Labs hands. So even before we got our hands on the real Atlas, we participated in the virtual challenge using Gazebo and the DRC Sim package to simulate Atlas and the challenge tasks. This was great because it allowed us a head start in developing for Atlas, and even now we test many things in Gazebo before using the real robot, since it's much faster to iterate on and it's a lot less expensive when Atlas falls over. That said, there are a lot of differences between the real Atlas and the one on DRC Sim. The inertial properties seem to match the real Atlas well. The joint torque limits and the sensor noise levels don't seem to match the real Atlas in our experience. So I think these are things that should be quite easy to improve on, and we hope to look into that in the future, and maybe see if we can make suggestions of what the actual value should be. So we've also been developing our own balancing controllers, and as we did that, we noticed a lot of contact chatter, which leads to a lot of noise in the force torque sensors in the ankles. We haven't yet experimented with the new physics engines that are available in later releases of Gazebo, so that's something we hope to try soon. Continuing in order of things that are increasingly hard to fix, DRC Sim gives you perfect torque sources in the joints within limits, whereas the real Atlas is hydraulically actuated with significant friction that leads to hysteresis, which is hopefully visible in this diagram of the actuator effort versus the achieved joint angle. So that's been especially significant in the development of our compliant controller that uses direct control of the electrohydraulic actuators. That said, now that we have the compliant controller, we actually have something that behaves a lot more like a direct torque source. So everything that's developed on top of it, we can test more directly in Gazebo. But I think something like this would be reasonably straightforward to emulate inside the Atlas plugin for Gazebo. So that's another thing to look into. Finally, Atlas comes with built-in behaviors for balancing, stepping, and walking. And during the VRC, these work fine in Gazebo, thanks to a binary blob shipped by Boston Dynamics. Unfortunately, when the real Atlas shipped, the DRC Sim models were all updated to match the real final version of the robot, but Boston Dynamics didn't update their binary blob. So the mass, for instance, of Atlas and the center of mass are all different. And so the old walking controller doesn't work anymore. You can always switch back to the old models, and then the walking works in Gazebo, but all of our own behaviors would behave in unexpected ways. So that's something I don't think can be fixed very easily unless Boston Dynamics decide to ship a new version of their controller. So once the real Atlas was delivered, we started trying to make it work with our software. The multi-sense head and the Sandia hands already have ROS drivers that match the DRC sim interfaces. Atlas itself ships with an API but no ROS support. So one of the first tasks when we received the Atlas last August was to create a ROS interface. And we created a ROS API that more or less matches the DRC sim one. We started by hacking on the example code for the API, intending to replace it with something better soon. So of course, it always happens, we're still using the same thing a year later. So on top of the basic ROS API for Atlas, based on joint commands or Atlas command messages, we wanted a way to allow multiple nodes developed by different people to be able to control subsets of the joints and hand off control to each other in a safe way. We have an abstraction layer called the low-level joint controller that is the only node giving joint commands directly to Atlas. Now, other nodes make service calls to register with it as behaviors, and each behavior is a node that accepts actions and can then ask the low-level joint controller for temporary control over a subset of joints. These invocations can be short-lived, as in the case of recorded trajectories, or long-lived, like a continuously running balancing controller. We've recently added an option to control each joint by either position and velocity control or compliant position control. So here's a short example of Atlas using compliant control on the arms to grab an egg. And it can grab other objects as well. So based on the force torque sensors in the wrists, it can gently grab anything, and that'll be part of our demo later. So as part of the simulated disaster response scenario, communications between the operators and the robot are severely restricted. The machines on the robot side are called the field computer, or FC, and the machines on the operator side are the operator control station, or OCS. DARPA imposed latency and bandwidth restrictions between the FC and OCS, with the exact methods and restrictions varying as the competition has evolved. During the virtual challenge, we had a limit on the total number of bytes sent and a limit on the total number of bytes received during one attempt at one of the tasks. We were just talking TCP/ROS over the limited connection, and our field computer nodes were running in a cloud server instance, and our local machines connected to the remote ROS master as well. Obviously, ROS isn't designed to be used this way, and there were many topics that use a lot of bandwidth. So as we encountered topics that were particularly problematic, we would find some workaround for that topic and move on to the next. Typically, we'd create services that would poll the remote end for a snapshot of the data we were interested in, as configured by a local user interface. Topics that were particularly problematic, though, include the clock topic, since we were running in Gazebo. So we tried remapping the clock topic, but that doesn't actually work with ROS CPP, as it turns out. So we ended up manually clearing the use sim time parameter after launching the remote nodes and before launching the local ones. That was quite horrible. So this whole setup was quite error-prone during actual operation, since the task of managing network resources didn't at all mesh with anything else that the operator was concerned with at the time. And we know from the forums that we weren't the only ones to try this approach of using ROS to communicate directly over the restricted network connection, and it didn't work too well for us. So it was far too easy to introduce new topics that would use up a lot of bandwidth. So for the next iteration, we went for an approach based on explicit whitelisting of topics between two distinct set of ROS nodes with their own masters. On each end, a node called ROS net tunnel is started. It reads a YAML file for initial configuration, and it establishes a link between the two ends. The configuration file can specify both a rate limit and a bandwidth limit per topic, and topics can be set as reliable or unreliable. It uses ROS topic tools to forward messages without having to deserialize them. I actually found that with a few extra template specializations, you can also forward ROS service calls transparently without having to know the service definition. But I decided against forwarding services in the net tunnel because making service calls when you know you're going to have a high latency seems like a pretty bad idea. Similarly, since we knew we had low bandwidth, forwarding dynamic reconfigure didn't seem like a great idea. We could forward ROS parameters. We haven't found a need for it yet. And finally, we support a special syntax in the YAML file for actions, which just generates the 5 topics in the 2 different directions required for each action. So that was our approach in Miami. I've recently learned of WPI's package, so that's something to compare it with. This was only an approach for controlling the topics between the 2 ends. It doesn't deal with by itself with compression or anything like that. Another thing we developed is a tool called HQMake. This was to help the transition from ROS build to Catkin. You can give it a package name or a list of package names, and it'll invoke the appropriate build commands in the correct order. It also speeds up the configuration step for Catkin packages by using the whitelist feature, so only relevant packages are configured. And most importantly, it uses cowsay to report build output. Next, we've been recently using Smash to develop some state machines for demonstrations. It's very flexible, and we've been able to wrap everything from action requests to command line tool executions and messy topic-based workflows that we hope to transition to action servers in due course. There are many stages where it's not possible to operate fully automatically, so our state machine will stop and ask the user to visualize the next step and intervene manually if necessary. So I'm going to take you through the stages in one of our state machines, which is the grasping demo that you'll be able to see later today. So the first step after we have Atlas booted up and safely on the ground is to initialize our localization node. This uses the laser scanner to track the position of multiple planes. The user helps it identify the planes of interest by selecting patches on each plane. And after that, the node can track them without further user intervention. It then uses these planes to estimate the position of Atlas and publish a map frame. It continuously fits the plans to the laser scans using Ransack. It can track the position of the robot to within a few centimeters, which is close to the accuracy of the Hokuyo laser itself. Currently, this only works in our lab, but we hope to extend it to other environments in the future. The next step asks the user to pick a destination for Atlas. We have an interactive marker that shows the workspace for one of Atlas's arms, and we can move it around so that the workspace covers the region of interest, in this case an object that we're going to pick up. The marker's position then gives us a goal for the next step, which is walking. So based on the walking goal and the current position estimate from the map frame, our walking node computes a sequence of steps in several segments that can include turns, large steps forward, and small correction steps. Since the walking is only accurate to a few centimeters, after executing each segment, it re-evaluates its current position and recomputes the subsequent segments to reach the goal until it's satisfied it's close enough. And at each step, the user can visualize the planned steps, and in case of problems, can interactively enter steps using an Xbox 360 controller. So here's a short clip of the walking. One of the utilities we developed very early on is a tool called Playfile, and this is simply a YAML format for saved poses and trajectories, and a command line tool that reads these files into a joint trajectory message and invokes an action server. We can also specify for each joint whether it will be controlled by position control, compliant control, or not affected. It's a simple tool, but we've made a lot of use of it for quick experimentation and for tying things together. At this stage in the demonstration, we use it to move the arm into a pre-grasp pose without knocking over the object we're trying to grab. So one interesting thing we've been able to do with the Sandia hands is use the built-in stereo cameras to reliably grasp an object. We use ICP to match a model to the point cloud coming from the hand cameras, and that allows us to reach the object much more accurately than if we use the head, because we're eliminating all the position error from the joints in the arm. So at this stage, we've got the hand in what we expect will be a good position for the cameras, and the user can check that the camera has the object in view and move the hand around in the camera frame to give it a better view if necessary. So now, if the point cloud and the position estimate for the object all look reasonable, the user can approve an automatic approach. Otherwise, the goal can also be set manually with an interactive marker. So once the goal for the hand has been set, we invoke an action client specialized for small, accurate movements to move the hand to the goal. If everything looks good, the user can then close the hand, and we make a second small local movement to raise the object, and then we execute another safe trajectory to hand over the object to a human operator. So I've got time left. I'm going to also quickly mention we have made use of Moveit. We used it in Miami, and it got us a point on the door task. We aren't using it right now because unfortunately all of our Moveit experts have moved on to other projects. So, so in our experience, I think that the planning component of Moveit is definitely something I want to reintegrate in the future. We don't have any type of planning at the moment. We did encounter problems with the interactive user interface for Moveit. One of the problems is that actually Atlas's arms only have 6 degrees of freedom, and it's very easy to bind it into awkward positions. So when you're moving it around with the interactive markers, it can be quite difficult to reach a destination. Actually, in terms of interfaces, we've tried a lot of different things for specifying a goal. And I think specifying where the object is that you're interested in and then automatically computing the pose you want to reach is a much more efficient approach in terms of just the amount of time it takes for the user to specify it than trying to manually move the hand in RViz towards the object. So that's it for this talk. After the lightning talks, we'll be running a demo several times, and you'll be able to see many of the tools and behaviors I've mentioned today put into practice on the Atlas. Thank you.